Imagine this. Picture a world brimming with devices, not just your phone, right? But like the sensor on a factory robot, maybe your smart doorbell, even a simple light switch.
Everywhere.
Exactly. And they're not just, following orders. They're actually thinking.
Perceiving, deciding.
Yeah, perceiving their environment, making critical decisions super fast, like in milliseconds, learning, even collaborating with other devices.
It's all happening locally, right there.
Right there on the spot.
Yeah.
Silently, autonomously. Now, it sounds maybe a bit sci-fi.
It does, a little bit.
But this is, well, it's rapidly becoming real. And it's all being driven by this quiet but kind of massive transformation in the brain of our digital world.
The microcontroller unit, the MCU.
Precisely, the MCU. So today we're doing a deep dive into this pretty profound reinvention of the MCU.
And how it's really kicking off a revolution in what we call edge AI.
Yeah. And our mission for you listening is basically to pull out the most important bits from, the articles, the research forecasts, industry insights we've gathered.
To give you a clear picture.
Exactly. A clear, comprehensive understanding of how these tiny chips are becoming the actual intelligence at the very edge of our networks.
Think of it as a shortcut, maybe?
Yeah, your essential shortcut to getting up to speed on this, well, quietly powerful shift.
And what's really, I think, game-changing here is that we're not just talking about, slightly faster chips.
Right, not just incremental stuff.
No. This is a complete re-architecture. It's a fundamental rethink of where intelligence operates and how.
Okay.
It's about decentralizing that processing power, pushing sophisticated AI capabilities right down to the device itself.
Which changes
Yeah.
everything, really.
Yeah, fundamentally changes how we interact with tech, how our infrastructure works. The scale is huge.
You've really set the stage there.
Yeah.
It makes you wonder, though. For years, wasn't the cloud supposed to be the answer? All that massive processing power up there.
That was the narrative, for sure.
So what's genuinely driving this big move towards edge AI? Why pull intelligence away from those giant data centers and, closer to the action?
What are the limits the cloud hits?
Yeah, exactly. What problems is edge AI solving that the cloud couldn't?
Well, a huge catalyst, maybe the main one, is just the sheer number of connected devices exploding everywhere.
Right.
IDC reckons we'll hit over 55 billion IoT devices by 2025. That's a lot.
55 billion, wow.
And get this, over 30% of those, they're expected to be in industrial settings.
Okay, so factories, production lines.
Exactly. Imagine automated lines processing thousands of data points every single second.
Hey.
Trying to send all of that data constantly up to the cloud, it's just not feasible.
It breaks down, right?
Yeah, and it introduces at least 3 really critical challenges.
Okay, what are they?
First off, latency, the delay.
Right. The time it takes.
Yeah. In industrial processes, think robot collaboration or maybe spotting a fault on the power grid. You often need responses in less than a millisecond.
To prevent bad things from happening.
Exactly. Accidents, system failures, sending data to the cloud and waiting for an answer back, just way too slow. Unacceptable delays.
Okay, latency is number 1. What else?
Number 2, power consumption and cost tied together.
Makes sense. Especially for small devices.
Totally. Constantly transmitting loads of data just drains batteries like crazy.
And costs money for the data transfer.
Right. Think about remote sensors, things out in a field, or smart meters. They need to run for years on a single battery.
Can't be phoning home every second.
No way. Edge computing, processing locally, can slash that data transmission energy need by 90%.
90%, that's huge.
It's a massive saving. And then the third big one is data privacy.
Always a concern.
Increasingly so. You've got sensitive data, maybe machine settings in a factory or personal health data from a wearable.
Stuff you don't want flying over the public internet if you can avoid it.
Precisely. Processing it locally, right there at the edge, significantly cuts down the risk of leaks during transmission.
Okay, so latency, power and cost, and privacy. Those are some serious bottlenecks for the cloud model in these scenarios.
They really are. And if you zoom out a bit, you see edge AI isn't about, killing the cloud.
It's not replacing it entirely.
Not at all. It's more about a smarter division of labor, redefining where certain computations happen.
The urgent stuff, the private stuff, the power-hungry stuff stays local.
Exactly. Bringing the AI right to the data source.
Yeah.
And this kind of hybrid approach, it's opening up enormous new market opportunities.
I bet.
ABI Research, for example, they're forecasting the global edge AI chip market to soar past $20 billion by 2027.
20 billion. Just for the chips.
Just the chips. And over half of that, industrial and IoT applications.
Wow, that really underlines the economic push behind this whole shift.
Absolutely. It's not just technically necessary, it's becoming economically vital.
Which brings us back to the hero of the story, kinda, the MCU.
The little chip that could.
Yeah, the traditional microcontroller unit, was just a simple controller for basic tasks.
Spin this on, turn that off.
Right. Now it's morphing into this central AI brain, capable of, sophisticated thinking, inference.
And we're seeing pioneers really pushing this. You mentioned GigaDevice.
Yeah, GigaDevice or Omro in China. They're a great example of a company really driving what these MCUs can do now.
And there's some context there too, right? With China's focus on domestic tech.
Definitely worth noting. China's domestic substitution strategy, partly driven by geopolitical stuff, has really created fertile ground.
An opportunity for local players.
A big one. And companies like GigaDevice have jumped on it. They talk about this end-edge cloud collaborative strategy.
Okay, break that down. End edge cloud.
So end is strengthening the computing power right on the device itself. The sensor, the actuator.
Got it.
Edge is enabling intelligent collaborative decision-making among devices locally.
So devices talking to each other, figuring things out.
Exactly. And then cloud is still used, but more for the bigger picture stuff, model iteration, refinement, learning over time.
Creating a loop. Data, local action, cloud learning, better models pushed back down.
Precisely. It's a seamless flow. Data collection, real-time action, cloud refinement, smarter action next time.
Clever. Any specific example?
Yeah, they have this DC arc detection solution. Think like spotting potential electrical fire hazards super early.
Critical safety stuff.
Totally. It performs deep learning analysis on, get this, 12 channels of analog signals
Okay.
within 0.6 milliseconds.
Wow! That's fast.
Incredibly fast. And crucially, without sending that sensitive electrical data up to the cloud, it all happens right there on the MCU.
That's local intelligence making a real safety difference in real time.
Exactly. And that commitment to local real-time smarts is kind of baked into another key part of their strategy. Their dual architecture approach. They use both ARM and RSCV.
Ah, interesting. ARM and RSCV. So why both? What's the thinking there?
Well, it seems pretty strategic, actually. It's about offering versatility without, compromising. So ARM is the proven workhorse, right? It gives you that industrial-grade stability, predictable performance you need for critical systems.
Yeah.
Reliability, precision.
Okay, the safe bet for tough jobs.
Yeah. But then, by also embracing RISC-V, which is an open-source instruction set.
More flexible, customizable.
Exactly. They tap into this whole ecosystem that's all about flexibility, customization, rapid innovation, which is perfect for the incredibly diverse, fast-moving world of IoT.
So you get the best of both worlds. Rock solid for industrial, nimble for IoT.
That seems to be the idea. It lets them cater to a huge range of needs, from really robust industrial control to, smart home gadgets. Makes them pretty strategic players.
That dual approach does sound smart, covering all the bases.
Right. Stability where you absolutely need it, flexibility where you want it. Okay, so let's unpack the nuts and bolts a bit more.
The tech itself.
Yeah. What are the specific hardware and software innovations actually making this happen? These are the tools literally building this edge AI future.
Hardware first.
Let's start there. It's not just about making chips small. It's about packing incredible power and precision into them.
Like their flagship MCUs.
Yeah. Take the GD32H7 series. We're talking 600 megahertz main frequency, which is pretty fast for an MCU.
And it has a dual precision FPU.
Right, a floating point unit. For handling complex math quickly. This means it can actually run lightweight versions of AI models, like YOLO 3 object detection.
Directly on the chip. No cloud needed for that.
Directly on the chip. And crucially, it uses something called an AXI bus. Think of it like a super efficient internal data highway.
Okay.
It allows for parallel operations. So grabbing data, running the AI inference, and sending out control commands can all happen much faster, almost simultaneously.
Getting latency down to microseconds.
Exactly. Microsecond level responsiveness.
That ability to run something like YOLO 3 visual AI right on the device, that's huge.
It really is.
Instant visual intelligence. Systems can see and react immediately. Think about safety in factories, like you said. Immediate object recognition, avoiding accidents.
Totally. And beyond just the raw speed, true edge AI needs incredible precision when it's, interacting with the real physical world.
Reading sensors accurately.
Precisely. That's where advances in what they call precision signal processing come in.
Okay.
The GD32H7, for instance, has 12 independent ADCs, analog-to-digital converters.
Converting real-world signals into digital data.
Right. And they can do multi-channel synchronous sampling at 500 kilosamples per second. That ensures super high accuracy and avoids things like phase distortion.
Which is critical for reliable measurements in industry.
Absolutely critical. Going back to that DC arc detection example.
The 0.6 millisecond one.
Yeah, that level of precision is why it can output results that fast, with 100% accuracy, they claim, and cut power use by 60% compared to older DSP solutions.
So faster, more accurate, and uses less power. That's a win-win-win.
Pretty much. Then, okay, you've got these smart, precise devices. How do they talk to each other in the network?
Connectivity.
Connectivity is key. Their GD32 VW553 chip integrates both Wi-Fi 6 and BLE 5.2, dual mode.
Wi-Fi 6 is the latest standard, right?
Right.
Faster, more efficient.
Yeah, and it's not just about raw speed, though it offers up to 600 Mbps in the 2.4 gigahertz band. It has tech like 24 QAM and OFDMA.
Okay, what do those mean in simple terms?
Basically, they let devices handle massive amounts of data much more efficiently and reliably, even when lots of devices are talking at once.
Like in a crowded smart home or factory floor?
Exactly. Think streaming real-time 4K video or handling data from tons of sensors simultaneously. Wi-Fi 6 makes that much smoother.
That robust connectivity plus the precision signal processing, that really unlocks new application types, doesn't it?
It really does.
High-fidelity data from cameras, from complex sensors can be processed right at the edge, keeps the data clean, reduces the load on the central network.
Yeah, and then for the absolute backbone of, like, automated factories.
Industrial networks.
Real-time industrial networks. They have EtherCAT slave control chips, for example. These can achieve synchronization times between devices of less than 1 microsecond.
Whoa, that's incredibly tight synchronization.
It is. Imagine robots needing to move in perfect split-second harmony. This makes it possible. Hundreds of sensors and actuators coordinated with extreme precision.
And that has real-world benefits.
Big time. They cite examples like reducing production line modification costs by 30%.
Because it's easier to integrate and coordinate new equipment.
Seems like it. And improving motor control response time from maybe 20 milliseconds down to just 5 milliseconds.
Faster reactions, more efficient movement.
Which also lowers energy consumption, in this case by 15%. So faster, cheaper to adapt, and more energy efficient.
Hardware sounds impressive, but hardware is only half the story, right?
Absolutely. You need the software tools and the ecosystem to actually use all that fancy hardware effectively.
Making it accessible for developers.
Exactly. GigaDevice's embedded AI toolchain, for instance, seems designed to really simplify AI deployment on these MCUs.
How does it work?
Developers can basically upload their AI models, maybe built in TensorFlow or PyTorch.
Common AI frameworks.
Right. And the toolchain takes that model, optimizes it specifically for the target MCU, and then generates efficient C code for them.
So it automates a lot of the tricky optimization and porting work.
That's the idea. They claim it can cut AI function development cycles by 40% and reduce mass production costs by about 25%.
That's significant, lowering the barrier to entry.
Definitely. And then for devices to get smarter with use, as they put it.
Learning and improving over time.
You need over-the-air updates. OTA.
It's pushing updates wirelessly.
Yeah. New AI model parameters may be refined in the cloud based on real-world data, can be pushed down to the devices.
But isn't sending whole new models data intensive?
Good point. They use differential compression, so only the changes to the model are sent.
Ah, much smaller updates.
Yeah, often just 5 to 10 kilobytes of data, enough to improve the AI's accuracy by maybe 3–5% with each update cycle.
Making the devices progressively better without huge data overhead. Smart.
And finally, they have an open-source hardware platform too, the GD32 IoT Evil platform.
For prototyping and development.
Exactly. It bundles together core boards, sensors, communication modules. The goal is to cut down the trial and error cost for developers working on AIoT projects, say by 70%.
That's a big help for experimentation.
Yeah, and it comes with over 10 built-in AI models to get people started. Apparently, it's been used in over 5,000 projects already.
Wow. Any success stories?
A remarkable 15% of those projects have actually converted into commercial products. So it seems to be genuinely useful.
You know, what's really revolutionary here when you put the hardware and software together is how it's just fundamentally lowering the barrier to entry for developers.
Making complex AI more accessible.
Totally. Sophisticated edge AI becomes feasible even for smaller teams, for niche applications, people who maybe couldn't afford the R&D before.
So it's not just making better chips.
No, it's about democratizing AI development for the edge, making it way easier, way more cost-effective for a much wider range of innovators.
Okay, so we've covered the why, the cloud limits, the need for local intelligence,
Yeah.
and the how, the hardware and software innovations.
Right.
Now let's bring it home. What does this actually mean for you, for the world around us? Where are we seeing the impacts?
Because the impacts are already happening, right? This isn't just future dazing.
No, definitely not. In the industrial world, for example, we're seeing a huge shift towards AI predictive maintenance.
Moving beyond just fixing things when they break.
Exactly. Moving from reactive fault repair to proactive risk prediction, using chips like the GD32H7 with their speed and AI models like CNNs.
Convolutional neural networks, good for signal analysis.
Right. Systems can analyze electrical signals in real time, spot those tiny microsecond-level arc waveforms we talked about.
Within the 0.6 milliseconds.
Yeah, and predict electrical fire risks before they happen. That's a massive boost for industrial safety.
Huge. And presumably similar benefits for energy management.
Absolutely. Moving from just passively watching energy use
Right.
to actively predicting needs and optimizing efficiency across that whole end-edge cloud system.
Making factories smarter and safer.
Definitely. And then for IoT and smart homes, the changes are maybe even more direct, more personal for people.
How so?
Well, that advanced connectivity, the Wi-Fi 6, the BLE 5.2, and chips like the GD32V W553, it's powering better, faster, lower power applications. Smart homes, wearables, medical devices,
Making them more capable, more reliable.
and enabling much more intuitive human-machine interaction, especially with voice AI.
Talking to our devices.
Yeah. Take a voice learning pen, for instance, using a GD32H7. It can do offline speech-to-text, real-time pronunciation correction.
Offline, so no internet needed.
Exactly. With 95% accuracy. And, crucially, the voice data stays local, which is huge for child privacy.
That is a big deal, processing sensitive voice data locally.
Or think about smart home devices using the GD32W515 chip. They support wake word-free interaction.
Meaning you don't have to say, hey, Google or Alexa first.
Right. It can listen for multiple command words simultaneously, offers control from up to 8 meters away,
Impressive range.
and gets the standby power is just 2 milliwatts.
Tiny.
Which means potentially over 2 years of battery life for a voice-controlled device.
Wow. That ability to run sophisticated voice AI locally,
They collaborate.
yeah, they collaboratively figure out the best irrigation strategy based on combined real-time local data, achieving maybe a 35% increase in energy efficiency through that shared local intelligence.
Wow. So the intelligence is spread out working together?
Precisely. And if you connect that to the bigger picture, the broader trajectory,
Yeah.
we're heading towards a future where basically every MCU is an independently evolving intelligent node,
Evolving. Learning on its own.
capable of real-time dialogue, collaborative learning within its local network, dynamically adapting. It's about building this ubiquitous, self-optimizing, intelligent ecosystem.
Intelligence woven into the fabric of everything.
That's the vision, where devices aren't just products you buy, but active, learning, collaborating participants in an intelligent world. That's terminal as a service.
Okay, we've covered a lot today. We've
Yeah.
taken this deep dive into how microcontroller units are undergoing this radical evolution.
From simple controllers to smart brains.
Yeah, from just executing commands to becoming these silent, smart brains driving edge AI. And it's not just about speed, is it?
No, it's fundamental.
It's fundamentally reshaping our industries, making them safer, more efficient, making our homes smarter, more private, making our devices just more intuitive.
By putting the intelligence right where the data is generated.
Exactly, right at the source.
And the implications really are immense as these tiny chips get smarter and more connected.
They're laying the groundwork.
They're laying the groundwork for truly distributed intelligence, where devices don't just react anymore, they anticipate, they learn, they collaborate. It really promises to redefine our relationship with technology in our environment.
So what does this all mean for you listening? Just think about how many devices in your life right now have an MCU inside,
Yeah.
quietly doing its job.
Probably dozens, maybe hundreds you don't even think about.
Right. Now imagine those devices not just controlling a function, but actually thinking, learning, and collaborating with each other autonomously.
Right there. No constant cloud connection needed for the core intelligence.
Exactly. This quiet but incredibly powerful shift. It's going to redefine what's possible. It's creating a world where truly everything can be a smart thing.
Delivering intelligence exactly where and when it matters most.
So definitely keep an eye out. Watch how this quiet revolution continues to unfold all around us. It's happening faster than you might think.